So now we have Dr. Tri Astrostatistics. Yeah, we can start the lecture. So Dr. Tri Astrostatistics, please. And now the time is yours.
Okay. Hello. Yeah. Thank you, Lucky. And hello again, everybody. Good morning. So today we are going to continue some aspects about regression. So you already know. You already got an introduction from Professor Feigelson earlier, and today I'm going to talk a little bit more details about some aspects of regression. So once again, let's pull up the slides. Okay. If I go full screen, can you see the whole screen or just some part of it?
Yes, we can see it.
Right, yeah, regression. So you probably know already what does it means when we're doing regressions. But I'm going to start anyway with talking about regression using probability theory that we already discussed yesterday. So we are going to see regression in a probabilistic manner. So here's an example of a data that we're going to work with during the whole our discussion. It's just normal points. So this is usually what people report when they're reporting results from regression. You have the points, and there's an error bar here, and this is the line, and then there's this area here saying the credible interval. 3 sigma, and here's said here is 3 sigma, which means, as we have seen before, it's about 99.7%. We are 99.7% sure that the points lie between this shaded area. So that's regression in general. We want to fit a model that we think is a good this description of the data. But in more general terms, we actually want to find theta that best fit the data. So we have a function here, and we want to find its parameters theta. So we have to define what is best, what is good. So this is actually a choice that we can make.
I'm sorry, I think your screen is freeze, so it's not moving to the next slide. Oh,
yeah, we're still in the same. Still in the same slide. But you can see me moving my video. There's no lag. Yeah. So what do we mean by best? It's we want to find parameters that here our choice is we want to find parameters that maximize the probability of getting theta when we have the data. So if we write them, if we write the probability, this is what we want. This is called posterior probability. We'll talk about it tomorrow in more details. But already going ahead of myself here. So this is what we want. What is the probability of theta given the data? And if we have seen the relation before, this is a conditional probability. Theta depends on data. The parameters depend on the data, and you can separate it as such. So the probability of the data given the parameters times the probability of theta. So we need the probability distribution of theta. There are names for this. This is called the likelihood. We already seen what the likelihood looks like, and then p theta is what we call prior probability. Now you probably already guess where we're heading here, but we'll discuss about prior probability, posterior, and everything tomorrow. So then the next question is, what is the appropriate likelihood and prior? And you probably already guess we're going to use Gaussian today, for reasons that you're going to see. So we can assume that that the data is going to lie somewhere between the two models that we want to infer, but they will have a scatter about the uncertainty, about the measurements uncertainty here with width of standard deviation. So we can use that as our likelihood. So we say that the probability to observe a single data point, given that the probability is 2, is a Gaussian here. So it's centered on the model, and it has a width of sigma. It's standard deviation. And then same thing like yesterday. The probability to observe all data is the product. We multiply all the probability of observing all of the data, so we get this product. Now, you can see here, I just remove all of the constant here. It doesn't depend on theta. Just to
Dr. Tri,
yes.
I think your screen, we still have only the title.
Oh shit! So sorry. So I already moved like 2 slides.
Oh, okay.
Okay.
Sorry, we still see only the title regression.
So you only see the title and you don't see anything.
Yes.
Oh,
for me.
okay. Okay. Sorry. How about this?
Okay. Now it's moving.
Okay. Yeah. And this.
Yes. Great.
Okay. So we can't do full screen. I'm sorry about that. I'm already in page 5. Sorry. Look. Right. Yeah. So this is what I said about regression. We basically want to. This is usually what we report when we're. Can you see the cursor? Try moving here.
Yes, we see it.
Okay, so you can see the cursor. Sorry about that. Okay, so yeah, so in principle, when we want to do regressions, we basically want to fit a model that we think can describe the data. So what we want to do is we actually want to find a set of parameters that best fit the data. So what we have to define, what do we mean here by best and best fit. So here I'm going to talk in terms of probability. So what we mean by best here is the set of parameters theta that maximize the probability of observing the parameters given the data set that we have. So that's our choice of what do we mean by best. So this, we have other criteria, but let's go with this. Yeah, so if we want to express it in terms of probability, this is what we want. We actually want to find this probability, the probability of getting theta, getting the parameters, given that this is true, the data set. This is called the posterior probability. So I'm getting ahead of myself here, so we'll talk about this tomorrow. And as you can see here, and we have learned yesterday that this is a conditional probability. So p theta, that's the probability of the parameters given the data, can be separated into this. So we can write it down like this. So it's the same as the probability of observing the data given the parameters multiplied by the probability distribution of the parameters itself. So they have names here. This is called the likelihood, and this is called the prior. Now, we'll talk about this in more details tomorrow. And now the question is, what is the appropriate likelihood and prior? Yeah, so the likelihood is a Gaussian. It's also a choice, but let's go on with this. So if as we have seen before, if we assume a Gaussian likelihood, that means the probability we assume that the data lies somewhere around the true model that we want to infer here in this line here. And the distribution of the true model, the point on the true model, has width of sigma here, standard deviation. So that's the expression for what is the probability of observing a single data point given the model. So now, same as before, the probability of observing all data set is the product of the probability of observing a single point, as here. Okay, so now we have defined the likelihood. So then next is we have to define what is the appropriate prior. And we haven't talked about Bayesian inference. So I'll just use the simplest prior of all. It's the uniform prior. That means we assume that the parameters can be anywhere. It doesn't favor a certain values. This is the most naive prior. It doesn't assume anything, but it also and it also the most what we call an uninformative prior. So that should be okay for now. I'll tell you. We'll discuss later why it's not okay. So, but for now, let's use what we call uniform prior. So if you use uniform prior, then the posterior here is just the likelihood. And same as before, we take the log of the posterior. And you can see the expression here. It's basically just a least square minimization here. Now, if we want to find the parameters that maximize the posterior, then same as before, we solve this for theta. Now, I think we already discussed this before, but let's just discuss some terms here. Look at this term here. This is called the sum of squared residuals, RSS. So that's why this is called least square minimization, because we want to minimize this guy here. All right. Then, yeah. So just to make a summary, so if you want to do the least square fitting, it's basically an inference of theta that maximizes the posterior. And if you look at the equation, it's clear that we're assuming the data is normally distributed on the true model. But also, if you look at the equations, there are also two additional assumptions here. If you look at the form of the posterior, we assume that the uncertainties are uniform. They all lie the same. They all more or less the same. And the parameters, we assume they are uniformly distributed. So that's what it is. So now, let's talk about the model first. You already heard about linear regression from Professor Feigelson here a few minutes ago. So and we have seen why it's called linear parameters, because it's just basically a summation of the coefficients that we want to find multiplied by what we call a basis function. So suppose we have an addition of basis function here multiplied by the coefficients, and a lot of forms, a lot of function can have this kind of form. So we have seen a linear straight line model. This is basically an addition of two basis function. So this is 1, and this is x, right, as described here. So the coefficient here, you can, this is just a 0 point, and this is the slope of the gradient. So another example of a linear function is a polynomial function, where here it's just the power of x. And that's the coefficient. Now, a linear model can be expressed in terms of matrices and vectors. Now, I hope you're not afraid of matrix and vectors, because I used to be very much afraid of thinking about matrix and vectors. I got nightmares about it. So, but I hope you're not like me. So I'm going to write this as a matrix. So you just multiply this matrix here and this factor here, right? So this is a row matrix. It just contains a single rows. It's 1 by p. So p is the number of parameters we have. And we multiply it by this column factor. But I transpose it here because if I write it vertically, it will look ugly. So this is actually just a column factor. It's a p by 1. And it has a name here. This x, it's usually called a design matrix. So now, if we can write this in terms of matrix and factors, then and if you're not afraid of it, I'm going to go ahead to write it down for the whole data, like this. So if you have a data set x and y, you can just concatenate or stack all of that row matrix into a lot of matrix of n with n rows here, right? And then the columns it goes across. It's just the basis function for each data points. So as you can see here, look at the indices. It goes from vertically. It goes from 0 to n. That's for the data. That's for the whole data set. And if you go across, that's for the basis functions. And we multiply again by this factor. Right. So if you can write that, then we can write the residuals like this. So you have the same. You have the column factor of the data to get the residual, and then we can rewrite the whole likelihood as the whole residual here as an inner product of the residual factor. So if you work this operation here, it's going to be the same as this one. Here this is a transpose. So that's the expression for of an inner product. Right. So now we know how. So now we know how to write everything in matrix. So now let's try to solve the log posterior. That's how you do it. And we have this expression for the of our estimate of the parameters. Now I'm going to put a hat here. If you like before, a hat, that means an estimate. It's not the two value. So it's just the inverse matrix of this times this. Right, so I'm going to give you a little bit of demonstrations. Okay, so there's going to be a code, right, that you can run yourself. And it's going to accompany this slide. So I'm going to send it later after this, so you can try it yourself at home. So we have a data set here. I just generate random data points around the two parameters around a line. We don't know the parameters of the line. Well, it's written in the code, but let's just assume for now we don't know. And this is just, but this is Gaussian noise, and the noise is uncertain, and the noise is has the same magnitude here. Right. So if we use the equation here to solve for theta, then that's the line. And you can see the residuals here, just to give you some idea. This is not the same scale as here, right? So don't be scared if it looks large. It's actually quite small. Right. So as before, we want to know how uncertain it is. So we already did this before yesterday. So let's try to see what's the likelihood, what's the posterior looks like in the data space. So this is the slope, and this is the 0 point, and this is the likelihood of this pair of points. So you can see the maximum is around here. So you can see this forms a curve here, and just as before, there's a width here. So we can find the width if you take the second, if you just expand it to the Taylor series, just like before. But now we do it in multivariables, right? Before we do it only in one dimension, but now we do it in many variables, as much variable as the number of parameters that we want to infer here. And so this is a Taylor expansion in multivariate. And as before, we know that this is 0 because we already defined it as such. okay, so we can get rid of this guy here. And if we just take the exponent, and we'll see this form. And as before, this is the same as a. This looks like a Gaussian, but looks there's this this term here, h. So what is this? This is what we call a Hessian. Yeah, and so this is a second derivative of the likelihood in all directions. So this is a matrix. So it's like a Laplacian, but the difference with the Laplacian is the summation of the second order derivative, but only in the principal axis. Now here there are more information here. This is the second derivative in pairwise. This is what we call a pairwise second derivative. So we calculate. So for each rows, we calculate the second derivative with respect to this pair of parameters. So that's what Hessian matrix looks like in p dimension. So this describes the curvatures in p dimension. Right. So so if we rewrite that in like a Gaussian, then we can see that this is the inverse covariance matrix, just like before. This is the negative inverse of the Hessian matrix. So we already calculate this before, and we already set it to 0. So if we differentiate it once more, we get the Hessian, and this is the form. Right. So that's the covariance matrix for our estimation of the parameters. So that's the expression for the covariance matrix. So yeah, let's discuss this a little bit. So as you can see, if you only want to infer the parameters, you don't really need this sigma terms here. This is the variance of the data, right? But if you want to determine the covariance matrix, we need to know the noise in the data. So, but in this case, we don't have it. So we do this by calculating the residuals. So we calculate the variance of the residuals like this. So if we plug it in here, if we plug this guy into here, then we get the covariance matrix. So so now we get the covariance matrix. We can predict. We know the parameters. We know the covariance matrix. We know how to predict new data and how to and what is the uncertainties. So it's just propagation of uncertainties, but it's in multidimensional. So you just add all of the partial derivative here on both sides. Remember, this is 1-by-1 matrix in the end, because we only predict single point. All right. So if you do this, then we can draw the credible interval. So this is like the data in the first slide. So this is how we do. This is how we do it. So this is usually what people report in papers or or whatever. So that's the model. This is the uncertainties. This is the data. That's the uncertainties of the data. This is what the residuals look like. This is I would say this is quite okay. Right. So now I'm going to show you what the two model looks like in the red line. So it's very close. Right? So it seems that we have a good estimate of the data. Why is it good? Well, because what we assume is the same as how the data is generated, this Gaussian noise. So it's pretty good. It doesn't really work like that in real life. So let's move on. Now, just as before, yesterday, what if we have individual uncertainties like this? So just like before, we don't put it outside, but we put it part of the likelihood, and then we do the same operation. But before, look at this term here. Yeah, here. Look at this guy here. If it looks familiar, because this is chi-square. So the log posterior is the minus chi-square. So this is why it's called least square is also called chi-square minimizations, because because we also want to minimize this. So here, there's nothing new here. We just we're seeing this in a probabilistic way. So that's what this is what chi-square minimization is. Just basically maximum likelihood, assuming Gaussian uniform priors, and also we assume the uncertainties also behave Gaussian. Right. So how do we write that in terms of matrix? So we can just write covariance matrix for the whole data. This is if we have n data. This is n by n, so it can be quite large. But if the uncertainties of each data points are uncorrelated, so then this matrix, although very large, is actually only consists of diagonals, which is the variance here. Right? So it's actually just a sparse matrix. However, if we make a measurements and we know how the data are correlated, then by all means, fill in the off diagonal components as well. Yeah? So if you know that kind of information, so yeah, so if we write them down, then the chi-square is just going to look like this. We've seen this before yesterday. Okay, so then we can solve the maximum likelihood parameters. It's just like this. It's the same as previously, right? But now there's this term here in the middle between the model matrix transpose and the model matrix. So now actually there is a weighting term here. So the weight is defined as the inverse covariance matrix. Right, and the covariance matrix, as usual, is this guy here. It's also the same. So now, as if the data are uncorrelated to each other, then that makes life simpler for us. The inverse of the covariance matrix is just simply the inverse of the diagonal components. We can rename this W. Right. So why do we care about all of this? All of these uncertainties, right? Because again, here we are assuming that the uncertainties are non-uniform. So if we force so here I generate a new data set, but now the uncertainties are non-uniform. So as you can see here, the uncertainties, they increase as x increase. So this measurements here is more accurate, and here it's more crappy. There are a lot more noise here. Usually, maybe this object here, maybe this data here is for fainter objects. So that's why our measurements of whatever it is not as accurate as when the object is brighter. So maybe that's the reason. But anyway, so if we are given this kind of data, and then we still think that if we still assume that the noise is uniform, well, we get the estimate here, but it's not, it's not really good, and it's quite different from the two values that are shown here in red. So, and also the width of the credible interval is somewhat large. So now, if we just use this information, the uncertainties in y, then we get a better estimate. So here I go back, and then this is the one where we assume the noise are non-uniform. See, it's somewhat closer to the true model, and also if you look at the credible interval, it reflects better of what we assume from this kind of estimation. You see here, the credible interval is more narrow than the one here, because it reflects what we know about the noise. Yeah, we know the noise here is larger than here, so the credible interval is also the same. So this is why it matters. You get if you know something, by all means put it in the model, and hopefully you'll get better estimate, as we see here. Again, this is because our assumption is the same as how the two data behave. Right. So this is this is just a geometric interpretation. How do we interpret? What does it means when we do least square in geometric terms? So suppose this is the true line, yeah, that we want to infer. So the data points in here will be scattered in a Gaussian way. So this is the Gaussian curve for this data point. It will be scattered vertically around this axis. So what we want to find is the parameter that minimizes the distance between the data. Let's say we observe the data here, and here, and the two line that we want to find. So we want to find the line, the red line that minimizes the distance between an observed point, let's say here, and the two line here. So here there is a point here, and we just want to find a line that minimizes the distance between the red line and this point. So that's the idea behind. That's the geometric interpretation behind the square regression. So this is from this book. By the way, this book is really good. I highly recommend it that you read it. And the book is free. So if you go to this link, you can download the book, the whole book, for free. So the copyright has already been released. This is not pirate. This is not pirated book. It's an original book, provided by the author. Right. So now let's talk about the meaning of the residuals that we try to minimize. So we have seen this before. So we assume there is a relationship between our data and a model, but then it's added by the noise. Yeah. So when we're doing fitting, we actually want to find the best function. Yeah. So that's why I give a hat here that minimize the sum of squared residuals. Yeah. So now this guy here, the sum of squared residuals, they can be written in terms of bias and variance of the estimator. So there's a lot of math here, but okay. But let's go to it. So here, this is the squared residual. Then the expectation value is like this. We have seen it before yesterday. So it's just the sum of the expectation value of y squared plus the expectation value of the estimator f here. And because y and f are different, and we can split them here. All right. So before we have learned that the variance has the form of this, and because we assume because the function here is the true function here is deterministic and the noise is additive, then we can say that the expectation value of f is actually f because it's deterministic. Now because here we assume to have zero mean, then the expectation value of the noise is zero. So from the equation, from the previous equation, the expectation value of y is f. So you can put it here. So some more derivations after 5 lines, you can see that the expectation value of the squared residuals can be decomposed of these 3 guys here. There's a bias. Bias is the difference between the value that we infer plus the minus the true value. So it's the difference between the inferred value and the true function, right? And the variance of our estimate. So normally, if we have we want to have a model that will give zero bias and zero variance. So right. So we want to have a model where this is 0 and this is 0. So the only noise remains is only the measurement noise. Now in general, it's impossible. So it's something that we cannot do. It's a fact of life. So what we can do is to characterize them. So we can try to find good models by try to minimize the bias, the variance, or both. So we don't actually know how to calculate this, right? Because this depends on the knowledge of the two model, but we don't know that. So that's a problem. So in principle, we will never know this value, right? Yeah. Only in simulations. life is good. But we can find something similar from the data itself. So we can calculate the root mean square of the residuals. We can calculate the standard deviation of the residual. So and then we can calculate the mean of the residuals. This is quite similar to before, but now this is all in terms of the data itself. So the root mean square, the squared root mean square, so the RSS, the sum of squared residuals, the mean, that will be that's the same as the variance of the residual and the mean, the squared mean, the squared. So we can see this as this is analogous to the bias, and this is analogous to the variance of the estimate. So, but now the noise, the third term, the noise, they all absorb into both of these. So we can characterize our fitting using these terms. Right. Yeah. So let's stop here a bit. Do you have questions?
If you have question, you can raise your hands. Any question? Yes, from Visa, please.
Hello.
Aside the plot you did, actually you mentioned the variance as 3 sigma. Why is the factor? Why is the factor 3? Like in the model, the variance was given as 3 sigma.
I can't hear you very well. Can you repeat while I'm? Let's see. Do you know which page you're referring?
So the graphs, the one you feed.
Which one?
So almost any of like almost all of them.
Okay, I'll keep going back.
So that is fine. Like the credible interval, there is 3 sigma.
Yeah.
Why is the factor 3 there?
Yeah, I just.
You can type your question, Visas, because we cannot hear clearly your voice.
Okay. Yeah, I think I understand. You asked why it's 3 sigma here. Is that correct?
Yes, that's it.
Yeah, so it's 3 sigma. It's a choice actually. I just want to show how big the uncertainties are so I want to show what is the 99.7 credible intervals between from the model. So you can do whatever you like actually here. So as long as you're very clear, about it. So you can do anything you want. If you want to do 1 sigma, which means that you're sure that your data will lie about 68% from the line, then by all means you can use 1 sigma. But I just want to show 3 sigma. So the choice doesn't really matter. There's really no conventions. But when you're reporting, just be clear about the credible interval. What percentage that we're talking about. So that's the answer.
Thank you.
Okay. Any more questions?
Thank you, Visa. Any other question?
Yeah.
Yes,
Go ahead, Yudis.
Thank you for the. I want to ask about predicting new data.
Yeah.
Is there any condition for the data trend to fulfill in order for us to make a prediction, or any kind of data? No matter how crowded is the data, we can make a prediction, predicting new data.
There is really no limitations. So let's say we do the same. We do experiment, and you get new data. Let's say here. So you can estimate. You can use it. Whatever information you have. However, as you can see, the data that we have is limited. you see it's only between about 0 and 100. What if you observe somewhere here or somewhere here? Are we sure that the model still holds outside this region? So that's extrapolation, and we cannot say anything for sure. So unless we observe something new beyond this line, then we can never be sure. So that's a problem. So you might say that oh, I observe new data here, and the uncertainties is here, this much. Just looking at the trend here, and then somebody or you make new predictions, and then actually it's here. Apparently there's a break here that we're not aware. So it's wrong. That's why we have to be aware of the limitations. This is so the model that we make, the generative model that we make is only as good as the data that we have, that we use to infer the model. So that's it. Just be careful about its limitations. Okay, I hope that answers your questions.
Okay, clear enough.
Okay, let's move to the next section. So if you have any other questions, just write it in the chat, or we can do it later. Right. So now the next topic is model selection. So now we know how to fit a model, right, to a linear model, to be precise. So now, but as you can see, our basis function can have a lot of form. Right? You have a straight line, you have a quadratic function, you have cubic function, polynomial functions. You can set up the order as much as you want. So how do we find the best model among the lists that we can possibly think of? So look at this data here, right? So I just generated a different data set from a secret function that we don't know what this looks like. So how do we do this? So obviously, if we do a straight line, then we can see this is not a good fit, right? It's obvious. But if we fit like a 20 order polynomial fit, so the basis function has 20 columns. Yeah, it goes from 0th power in x to the 20th power, and then we find the 20 coefficients using this data. It seems to work really well here. Look at this. It's exact. It hit the points exactly, right, in here. And this is doing reasonably okay. But here, this is not really working very well. So there's a case of what we call an overfitting here, because we have a lot of wiggle, because we have 20 wiggles to fit. So some of the data can be fit, can hit exactly the wiggles, but maybe some part of it cannot. Or if we have new data, let's say suddenly it's here, then it's terrible. So it doesn't. What we say is that 20th order fit can do a perfect fit, but it might not generalize to the general situation. So that's another problem. So is it somewhere in between, like this, like a polynomial fit? It seems to be doing well. Or perhaps because of noise. Yeah, we don't actually know how big is the noise here. Because of noise, it's actually just a quadratic fit, right? So how do we do this? So we have seen various methods that has been described earlier. There's AIC, BIC, there's this so and so test. So I'm going to discuss about cross validation. Yeah, so now cross validation is quite a nice technique. And if what we only care is prediction, about accurate prediction, then cross validation is a tool that we can use. It works like this. We split the data into two parts. So one is a training set. It's called a training set. And then the other is a test set. So the data is split into two blocks. Now So now for each set of models, we determine the parameters using the training set, and then we predict the values of the test set, and then compare it with the y's. So it goes like this. So this is the parameters that we get from the training set, and then we predict what is the value, and then we compare it with the data in the training set, and then we calculate the residual sum square. Right. So now there is also another approach. It's called the leave one out cross validation. So before, if we just split the data into two blocks, the training set and the test set, if we have a small number of data, like only 10, so we only have 5 data for training to determine the model, and then 5 to predict. And using only 5 data, we probably won't get a good fit. So one way to do it, so another approach is to split the data into as much number of data as it is. So here's an illustration. This is the block. So the blue one is the block that we use to test the data. To train the data. So the red one, we use the red blocks of data to train the model, and then we use one data point to test the model. So we do this for each. So we do the testing for each data point. This is why it's called leave one out cross validation, because we leave one data point for testing, while we use the rest of the data for training. So, and then we collect and we calculate the residuals of the testing each time. So if we have 8 data like the illustration here, that's probably going very quickly. But if we have 1,000 data point, and that's going to be quite lengthy. It can take quite a long time. So you have 1,000 data points. That means for a model, we have to do 1,000 parameter inference, and then we go on to the next model. So if you have 10 model, that means 10,000 calculations. And if the model, and if the parameter is can be quite a lot. So we can take somewhere in between. This is what we call a k-fold cross validation. So we just split the data into, let's say, 10 blocks. Right. In the first iteration, we train the data using this block of this fold, and then we test the training using this fold. And in the next, we use this fold for testing, and then all of the other for training, and so on, until all blocks has already been used as a test set. We don't have to do all of this manually. There are a lot of Python package or R package that can do this for us. So let's see how well our cross validation is for it. So here I use polynomial models as the testing, and then for cross validation I just use leave one out cross validation. So here for each panel, that's for the order of the polynomial. So here P is 0. That means just a constant is fit to the data. P is 1. It means just a straight line is fit to the data. This is quadratic function, cubic function, and so forth. And all of the green lines here, this is the results of the cross validation. So this is the fitting results for 25 data sets. So that's why there is really bad fitting when 1 or 2 data points leave out. But that's the point. So but on average, for example here, the models are here. So all of this has root mean square of the cross validation. So this is shown here. So the x-axis is for the order from 0 to 23. So from here, and the line here is for the root mean square of the cross validation. As you can see here, the minimum RMS is when we fit the sixth polynomial of the sixth order. Yeah, I think so. Yeah, so this is the best order. But this is the best polynomial order, and as you can see, it's not bad, right? Compared to this guys here or these guys here. This is probably ideal for the data. Now, of course, if we repeat the same experiments for a different set of data, we'll probably get a different order, right? For example, I increase the number of data. So now we have more data to deal with. See here, there are gaps here. But now this gap is filled, and also we have more data. So and we do the same experiment, and now the best order now is the best polynomial order is the 10th. So it's this one here. Now also not only because of the number of data, but also if we have less noise. So now here we generate a different data, but now we have less noise, 10 times as much as previous, 10 times less than the previous. And also we have also more data. We have 100 data, and now the results here is more decisive. Yeah, it's not only we have a different order, but it's also more decisive in this part. So it's here in between. So now we have a higher order. So that's cross validation, and this is the comparison between the two function here. Now I show what the two function looks like with the best model here. Here's the one with 25 data with the smaller number of data. So it's so it doesn't look the same. So there are discrepancies, there are differences here, but this is because there's a gap here. We don't know what the function looks like here. So we'll just guess based on our model. So, but of course, if we have more data, we have better accuracy, then our inferred function resembles quite closely to the true function here, to the true model. Now, of course, here again, going back to the UDIS questions here, we have to be careful about extrapolating. As we can see here, the inferred model goes up here, while the true model that we usually never know goes down. And here this also goes down, same, but not the same as before, because we don't have information here, right? So the model is just guessing. Of course, if we later on we have some more information here or here, we might probably get a better estimate. So, but for now, we do it quite okay using cross validation. Now, another concept that I'm going to discuss here is what we call a bias variance trade-off, and this is an exchange. Sometimes we cannot win both. Remember, a good model is where we have zero bias and zero variance, or at least the number is very small. So we have small bias and small variance. But sometimes we cannot get both. So when we are selecting model, there's usually a trade-off between bias and variance. As you can see here, when we increase the order of the polynomial, the bias increase. But at the same time, the variance also decrease. Honestly, or sometimes it's the opposite. We increase the complexity, the bias decrease, and the variance increase. So it's one or the other. So usually there is a trade-off between bias and variance. So the optimum one is the one where the combination, where the summation of both are at the minimum. So that's the deal. But of course, what we mean by a good model can be different from one person to the other. If we define a good model is one that is minimum bias, then by all means use this model. If it shows like that, or if what we want by what we mean by a good model is the model that minimizes the variance, and by all means use this part. So actually it's just a matter of choice. Just be aware about this. Aware about this phenomenon, what we call this bias variance trade-off. All right, so that's cross validations. So now let's move on to non-parametric regression. So I'm going to do this is probably not new, or you've heard a little bit about it. So I'm just going to describe it lightly. So the motivation has already been outlined by Professor Ferguson earlier. So we have to use kernels if we want to do non-parametric regression. And kernel is basically a weighting function. And the weight will depend on how far a point is from a data point. But then the distance between this point that we want to evaluate and the data is normalized relative to the bandwidth h. And this is something that we have to choose. What is the ideal bandwidth? So this is the derivation of the Nadaraya-Watson estimator. So there are other non-parametric regression out there, but let's use Nadaraya-Watson estimator. So in principle, we want to find a function that gives the expectation value of y at point x. So for that, we have to use the data point itself. So the expectation value, we have learned about this yesterday, of y. It's just the integration of y over the function that we want to find, and it has to be normalized. And the form of the function that we want to find is a KDE function, the kernel density estimation. This is the form of the function. So you already seen this, and just a bunch of derivations. But anyway, we want to find this integral. We also want to find this integral. If we work it out, we'll find that the numerator, the upper part, is this one. It's the weight of the y's. And here, and the bottom part, the denominator, is the summation of the kernel function. So then we have the function. That's what it looks like. This is the summation of the kernel times the data. So this is the data. So the data, the y's are smoothed by the kernel, and then it's normalized by the sum of the kernel. So we can rewrite them in terms of the sum of weights. It's the same as above. And this is how we calculate the uncertainties of the estimate. So the variance of our estimate at x, again, this is just the summation of the weight for each data point minus this summation of the residual weighted by the weight at x. So now we then have to find the bandwidth, the most appropriate bandwidth. But not only that, we also have to find the kernel function. So how do we do that? I'm going to let you guess. All right. So now let's think about it. Okay. So, but for now, let's talk about kernels. So kernels is just a weight function. It's a function of u here. That's a normalized distance relative to the bandwidth. And there's a lot of kernels there. You've heard of the Epanechnikov kernels. It's this guy here. And there's also a uniform kernel. So the weight are uniform within the bandwidth, but zero everywhere. There's a Gaussian kernel, which are non-zero everywhere. And a lot more. So you can look at this page to see what kernel out there. And there's a lot more beyond the page. But notice here, there are two kinds of kernels. The one where it's non-zero everywhere, like the Gaussians, right? So this is what we call kernel with infinite support. So support is the area where it is non-zero. Now Gaussians, they are non-zero everywhere. So they call it infinite support. And the one here, it's just defined within the bandwidth. So like the uniform or the Epanechnikov or the triangle kernel here. They have what we call a compact support. So they are non-zero only in a certain area. So, there are different reasons to use that. The reason is if we use Gaussian kernel or kernels with infinite support, that means far away data that are far away from each other, they can still influence the results of a point that are far away. So of course, the influence is very small, but it's still there nevertheless. So this can be undesirable. So otherwise, if we want only nearby data that influence the results, then we can use kernels with finite support. So that's the reason why there are two kinds of kernels like this. Right. Then, so that's let's try this with the same secret functions. Well, we already know what it looks like, but now we generate the same points here. Now we have 200 points, so we have quite a lot. Now, if you guess that we are going to choose the best kernel and the best scale lengths using cross-validation, you're right. So this is how we do it. So you already know how cross-validation works, and this is the results. That's the root mean square errors here for each bandwidth. So I just select the bandwidth between here. It's very short, and here it's very long. It's 10 units. While here it's close to 0.02. As you can see here, this is the area. This is the length, the scale length that gives the minimum cross-validation residuals. And yeah, and it looks like any kernel is fine. Of course, there is this. Of course, this uniform kernel seems to give slightly less RMS than the other, but honestly, there's not a lot of difference here. So that's what the estimator looks like. And, it's doing greens here, as compared to the two model here, which is in red, and that's the estimations. So that's uniform kernel, it's Gaussian, and so forth. So as you can see, there's very little difference between the inferred model and true model. So whatever kernel we're choosing, it doesn't really matter for this data set. So it works. It was fine. Notice here that the uniform kernel is quite jagged here. There's a noticeable break here. That's because the scale length is very small. As you can see here, the optimum scale length is only a little bit more than 0.1. So 0.2 or 0.3. So that's why it's only used maybe 1 or 2 data around the evaluation points. So whereas the Gaussian kernel here, it looks rather smooth. So for this data set, where we have 200 data, it's whatever kernels we are using, it looks okay. But if you have a different data, then the results can be different. So this is a problem for the Watson estimator. Is it totally depends on the distribution of the data. So if you don't have a lot of data or it's not uniform, then there might be gaps here because we don't have no data and because we use a finite support kernel. So the only information we get for this area is either this guy here, this data point here, or this data point here, and that's only up to a certain distance, right? As we have seen. So further than that, we have no information. So this is blank here. Here will be dragons, right? But if you use a kernel with infinite support, then this data here, they can still make some guess about what it is. But of course, that totally depends on the shape of the kernel we choose. So it's probably not really a good estimation. As you can see, it's quite different. So there are several ways to address this problem. First, we can use variable size bandwidth, one for each data point, or we try to do we try to estimate it using cross validation, but it's going to be highly dimensional. It's possible if you're feeling like it, or we just use the measurement uncertainties, or we can enlarge the fixed bandwidth here. We can just ignore the cross validation results, right? But as before, as mentioned before, be careful of over smoothing. It probably doesn't tell us much about the data if we use very wide bandwidth. So that's what I can tell you today about regression. So there are some additional thoughts that suddenly came to me. So fine tuning. So the bandwidth that we have seen here, the bandwidth H that we want to optimize, and also the polynomial orders here that we want to minimize, that we want to find, they are called hyperparameters. They are parameters that sometimes they are called hyperparameters. That's why you get this term here. They are parameters that we are not particularly interested in because the parameters that we want to find are the thetas. But nevertheless, we need to find them as well in order to optimize our models. So yeah, so we can use cross validations. However, as you might have noticed, we actually do what we call a brute force fine tuning. So we define a range where we think the hyperparameters might lie. So for example, here I think it's between 0.02 and 10, and then I set up a grid here. Yeah, and then I test them one by one, and then that's why we can create this line. This is brute force fine tuning. That's if we have small number of data, like here we only have 200, and if we only have one hyperparameter to fine tune, that's fine. And in fact, it's probably the best. But we might run into problem if we have two hyperparameters or even more that we need to fine tune. And there are a lot of models out there with many hyperparameters that we need to find. That can take a long time if we do brute force. This is the curse. This is what we call the curse of dimensionality. Right? If we have because the number of parameter combinations that we have to test will increase by the power of the dimension. I mean, for example, here, if we have 100 points between 0.02 and 10, and then we have another 100 points that we need to find out, then there's going to be 10,000 calculations. That's a problem. If we have 3, then that's even more. That's about 1 million. Loop that we have to do. So that's a problem. So we have to design an optimizer that can find the best hyperparameters, and for that we can use. There's a lot of methods out there. There's a gradient descent, but we have to calculate the second order differentiations. That might be tricky if we don't know what the function looks like. The MMS might be bad, and we have to calculate numerically. It's not very easy for difficult functions. Or we can use what we call a simplex method, the triangle method. So we don't need to calculate the differential, but it can be very slow, and we can get trapped in local minimum once again. So this is a problem, but it's much better than brute force if we have a lot of dimensions to deal with. All right, and then the second thing, so I think, just to give the big picture, when we are doing maximum likelihoods, people usually call them L2 minimizations. This is because the log posterior that you want to optimize, it has a residuals to the power of 2. So that's why it's called L2. This is also called an objective functions or a loss function. Right? The objective function is a function that you want to minimize in order to find the parameters. But L2 is not the only way to find the model. You can also minimize the absolute residuals, like here. So not the squared residual, but the absolute residuals. This is for L1 minimizations. Now, if it because this is absolute values, if we take differentials, there's generally there is no analytical solution. So we have to solve it by numerical methods. But why we want to minimize absolute residuals? Because generally it's more robust to outliers. But we also have some other ways to reject outliers, which we're going to talk in a couple of days. So that's everything that I can say. So we still have about 20 minutes for if you have some questions.
Okay, thank you, Dr. Tri. Any question? You can raise your hand. Yes, CJ, please.
Hello, Dr. Tri. So
Hi, CJ.
I have two questions.
Mm-hmm.
So my first question is, what's the difference between a confidence interval and a credible interval?
Okay.
And then the second question is, what do I do if, for model selection, what do I do if I want to penalize extra parameters? For instance, in the example that you have, the sixth order model was the best one according to the cross-validation, but it also has six or seven parameters. So we expect that it can accommodate more wiggles than the lower order. So how can we penalize extra parameters so we can follow Occam's razor?
Okay. Yeah. Yeah. Very good questions. Yeah. So the first one, it's just credible interval is just a different term. It's the same. So people like confidence intervals. It's the same, but I use and some people like to say credible intervals. It's actually the same. But people who use credible interval, they usually think in a Bayesian sense. So you already guess. You already guessed my perspective on statistics. Right? So, but it's just different terms. It's the same actually. It's basically as we have described yesterday. Credible interval is just the range of how sure we are that this point lies between this range. Don't worry about it. Now the second thing about penalization for complexity. Now the cross validation doesn't really care about complexity. So it's a very pragmatic way of testing models. So if it's so there is no penalization. It just minimizes the cross validation residuals. So if we add more wiggles and it doesn't predict nicely to new data, it doesn't predict new data very well, then it's automatically penalized because the RMS residuals gets very high. So you get the idea of cross validations, right? We don't use the data that we used to test for the parameter estimation. We leave that out. So if we have 10 data, we only use 9 data to find the parameters. Then we use the parameters to predict the value of the data that we leave out. We calculate the residuals. If the residuals is bad, that means that means the model doesn't generalize well to new data. That's the idea. So it doesn't really care about the wiggles or about complexity. It doesn't care about Occam's razor. So it just cares about how well our model is in predicting new data. So that's what the idea. if we care about penalization, there are other tests about it. There's the big, that's explicitly penalize model complexity. It's not without its weakness. We'll talk about this maybe tomorrow. So yeah, so then again, if we want, it all depends on what do we want out of it. And if you don't care about models, about complexity, outcomes rates, or whatever, I just want to predict values, right? Stock markets or whatever. I use cross validation. That's I hope that helps.
Thank you, Doctor.
Okay, thank you, CJ. Any other question? Please raise your hand.
Yes, please.
Any question? Fernanda, yes, please.
Okay, thank you for the opportunity for me to ask. Maybe I have two questions.
Okay.
The first is, in reality, do we actually use polynomial regression to fit our data? Because as we see earlier, if we use a different number of trained data, the order of the polynomial will varies, right? Or do we have to look back to the thing we are measuring, like what's the system or the object we are observing? And the second, is it possible for different models to mimic each other? For example, polynomial model with combinations of trigonometric functions or such functions.
Okay. Yeah. Thank you, Fernanda. That's also another important question regarding the choice of models. Yeah. So if we have physical motivations to use polynomial models, then by all means use them. For example, if we in astrometry, we use polynomials to transform between coordinates on an image into coordinates into the sky, and they all have physical interpretation. So the coefficients for the first power, just the first power of x, that means rotation and a scale. So they have physical interpretation. We can work with that, and we can calculate the plate scale. So of the chip of the image. So the higher orders, like the second orders, that correspond to an optical distortions in the radial direction. So and the third order is usually relates to lens problems like astigmatism or anything. So they can be so they have physical interpretation. So that's why in astrometry people use polynomials quite a lot, because there is a physical interpretation to that. So sometimes it's appropriate, sometimes it's not. So be careful, because polynomials can also model the noise. That's why you can see it can exactly fit the data. Of course, it doesn't generalize because of noise. And the second thing is, can models mimic each other? Yes, and actually, if you look at the code later, the function that I use to generate all of this data that we fit with polynomials, what are they? They are sines functions. They're sinus functions. But you can fit it with polynomials. So it's actually sine functions multiplied by some terms. Yeah. So functions, they can look like each other. So sometimes we don't know what is the true function, but if you want to be pragmatic and if the model can predict new data, then yeah, maybe it's the right one. So there are some ways to find out if it's the right model. But sometimes, you know, if it fits several criteria of a good model, maybe it's okay. Maybe it's the right one. So I hope that answers your
Yes.
question.
Thank you very much.
Thank you, Fernanda. Any other question? Yes, Abdullah, please.
Yes, thank you, Doctor, for your talk. I have a question about what is it called, the kernel.
Yeah,
So
not the Ray Watson.
yeah, there is, like you told us, there is for example, four ways, like the Gaussian and the uniform and the others. And I saw, like, for example, in slide number 63, the slide, like, how can I determine the best fitting for this data? And if I increase the number of the particles or for the point, is the fitting will going to change, and one of them will be more accurate than others, like as we see in the polynomial one, when we increase the number of particles, it changed basically. So how can I determine this?
Yeah, the short answer is cross validation. So you can do that. So for each time we have new data, or each time we want to find, if you want to test other kernels. Yeah. So as you can see here, this is we try 4 kernels. So each line here is for different kernels, and for the horizontal axis, it's for the bandwidth for each kernel. So as you can see here, the best kernel can also be determined. Yeah, it's a uniform kernel with this length. But as we can see, also it's not really dramatically different, right, for this data set. It might well be that if we have different data set and we do the same exercise, we do cross validation again, then probably other kernels might perform better. So it all depends on the properties of the data that we have. But yeah, here the best way to see it, in my opinion, is use cross validation.
Okay, thank you very much, Doctor.
Right. Yeah, hope that answers.
Okay, thank you, Abdullah. Any other question? Question? If not, Dr. Tri can Fitri. Okay. Yes, please, Fitri.
I want to ask, is the RMS is the only statistic to indicate the best result from the cross validation, or there are another statistic that we can use, like press statistic or such as that?
You mean for cross validation?
Yeah.
Yes.
The indicator is just RMS.
Yeah. You can if what we care about if what we care is about prediction accuracy, then we can use RMS. But there's a lot of other metrics out there, that we can also try. A lot of other test statistics, like the chi-square, like the we can also use that if we care about, let's say, uncertainties in the data. So we do the prediction, and then we use the test data, but we also normalize it with the uncertainties. So what we get is a weighted RMS or chi-square. So that's also possible. You can also do that. And there's a lot of statistics that we want to use, or let's say, for example, like what's called median absolute deviation, so just the mean absolute deviation. So there's a lot of choice there. Just be aware about what all of that means, right? And what does it tell you? Now the RMS, as I have as we have seen, it tries to optimize the bias and the variance between the model and the data. So that's what it's doing. It tries to find it wants to find the optimum trade-off between bias and variance. Now other test statistics, they might have they will have different meanings. So then again, we have to define what we want and then see what's this test statistics means to us, and is that a good test for our purpose? That's my opinion. So we have to do some digging about what does it all mean? Does it fit our goals? It's a little bit fake, but I hope that answers your question.
Okay, thank you for your.
Okay, thank you very much, Fikri. So we still have 5 minutes. Last question.
Last 2 or last 3 questions. If you have something.
Yeah, last 2 questions or something. If not, I want to ask question to Dr. Tri.
Okay.
So
yeah,
recently we see astronomical articles. So most of the articles using Gaussian process regression. What do you think about it? Is it the correct way to handle the astronomy problem?
Yeah, Gaussian process is very popular these days. I even use it, and everybody's using it. I think it's a good method of non-parametric regressions. So for those who are not familiar, Gaussian process is just like another Watson estimator, but now we use but the basis function is a kernel. So it uses all of the data, and then it's actually a linear model. It uses all of the data, and the basis function is the distance between the data points, and then we assume everything is Gaussian. Yeah, I think it's a great method. I think we have to try it once in a while and see what kind of science we can get. And I think one of the problems about non-parametric regressions, Gaussian process includes. It's very difficult to interpret what does this all means. It can make good predictions, excellent predictions, but the predictions sometimes it depends on the type of kernels that we use. But also, we are not trying to. It doesn't. Sometimes the models doesn't have really any physical interpretation. So that's one of the drawbacks if you don't have heuristic models. So just remember about the weakness. It is. But I like it. It doesn't pretend to know what's the underlying models. It's just want to make predictions. So try it once in a while. It's too bad we don't talk about it.
Okay, thank you very much, Dr. Tri. So last question. Any other question? Well, if not, maybe we can close this session. So thank you very much, Dr. Tri.